Deacon late. Deacon not get to go up a pulpit either. So Deacon just squeeze in at the back seat there beside him and say, and when Deacon take off him hat, him say, Deacon head ball too. Hear the parrot. So what happened? Sexual too. Of course, we tied it up. What we sexual too? So anytime you see a man with him bald head, you say, what you sexual too? Oh boy.
While the part I included Deacon.
What you sexual too? That's why he would be bald head, you know. All right. I want to tell man to start, you know. How many people we have so far?
17, sir.
I have 18 people so far, sir.
So we can start then. All right. So you guys remember from CXC when you shine light from one medium to the next, like you shine light from air to water, and the light appear as if it bend. You remember that?
Yes,
sir.
And we have, I believe, from that we studied Snell's law, right? Sine I over sine R equal mu, something like that. Anyway, going from the air to the water, two things happen. Some of the light go in the water and appear to bend, and some get reflected at the surface. Now, with electric field and magnetic field, the same thing happens. And we are going to study this today. We call it boundary conditions. Okay? So we're going to look at two conditions between a conductor and free space, and between two dielectric with different properties. Remember or recall Maxwell equation. The integral of E dot dl equals 0. And the integral of D dot ds equal Q. Or the closed integral of E dot dl equals 0 and the closed integral of d dot ds equal q. Now, imagine we have an electric field hitting the boundary at an angle. So you have your boundary and you have your electric field hitting the boundary at an angle. The first thing we want to do is what? What we always do. We always resolve the field into a tangential component and a normal component. Correct? We must know that by now, man. Because that's the only way we are going to be able to deal with it. Tangential component and a normal component. That is, if this is your boundary, and this is your field hitting the boundary at an angle, we are going to resolve it, the tangential component and the normal component. The tangential component, we say E tan. And the normal component, E with a little n. So E equal, so E would be your hypotenuse, and then you have opposite and adjacent. Tangential component and normal component. It's a vector, right? Adding two vectors. For later reference, or it should come automatic because D, your electric flux density, is epsilon E, right? So the same thing that obtains for E obtains for D. Now, let's do the first case. The case with a conductor and free space. The conductor is ideal having infinite conductivity. That means that the resistance in the conductor is negligible, like with copper, silver, gold, etc., etc. Very high conductivity of about 10 to the 6 Siemens per meter. The field intensity inside the conductor is 0, and the flux inside a conductor is 0. Meaning, if you don't have any resistance in the conductor, no field. Or the electricity travels along a conductor on the surface of the conductor. Right? The charge density within the conductor is 0. Thus, the electric field, the electric flux, the charge, the volume charge within the conductor is 0. Charge on the surface is what carry the current. So there is a surface charge density. All right.
Sorry.
Yes.
What this is saying, inside of the conductor, there's no current. It is on the surface of the conductor. That's what it's saying.
That's correct.
Oh,
Because the conductor have a high conductivity. So there is no electric field, no charge, no electric flux in the conductor. So when you apply a potential across the conductor, all the charge is on the surface.
okay.
Now let us look at this figure. Here we have your electric flux or your electric field. We are resolving it into a normal component and a tangential component. Let us do a little math. Give me a second, I smell my pot. I hope it, I think it'll boil over. Hold on. The pot cool. If you don't eat any, you could get lunch. All right. We're going to do something here now. This is your conductor, right? First thing we're gonna do, we're gonna create a Gaussian surface. So we put a cylinder around here, right? Cylinder, a delta height, and a delta surface at the ends. And this is your total Gaussian surface. Now, this is free space, and this is within your conductor. Okay? We are going to say, go to figure 5. Let's figure 511. Okay. We don't have any figure 511. All right, let's come back to this. But we are saying now, so E makes some angle with E is making some angle with the boundary. So again, we resolve it into the normal and the tangential. We know from Gauss' law that the integral E dot dl is equal to 0. So look at this now. Look at this square here. So the integral along the closed path. So if we choose a path here. So if the charge is here, and we integrate along any closed path, the integral of the electric field, E dot dl, along the closed path is 0, which is kind of understandable because if you move the charge along any closed path, you reach back at the same place, and so it don't travel no distance, so the work done is 0, right? So we're choosing this path from A to B, A to B, B to C, C to D, D to A. So the integral of E dot dl along that closed path is 0. Note that this and this are parallel. Now, the portion C to D is in the conductor. Where E is 0, because there is no charge within the conductor. So C to D is 0. No electric field. Right? Where was I? Okay. So we can drop out the integral of C to D. So we are left with this. We are going to do something now where we are going to shrink H so that this come up and this come down. So we are going to shrink it towards the surface. So E dot dl, A to B, B to C and A to D equals 0. All right. DL, if we move the A, the A to, if we move the D to A and the B to C over on the other side of the equation, we get this. E dl is delta W, right? We agree?
Yes, sir.
Delta W along the tangential direction of the boundary, in which the direction is E tangential. So E, A to B, A to B equal E, A to B, dl equal E delta W, because we move that over the other side. So E tangential then delta W, where E tangential is what? This. B and C, B to C is parallel to the normal component of E. B to C is parallel to the normal component. This is the normal component, or this. So E normal is this. For as you shrink delta H, as we shrink delta H, so we shrink this all the way to the surface. All right? So consider you shrink it so close that this side touching here and this side touching here. Where were we? Where were we? Where were we? Where? Okay. Over the small height, delta H, E normal can be assumed constant and can be taken out of the integration. So we are saying then that because it's so close, on the conductor side, it is this, you could say it's the same as on the insulator side or on the air side. So E normal A to B dl is equal to E normal C to B dl. So we are saying then exactly what I said before. A normal or E normal on this side, because we shrink it this way, is the same as E normal on this side. Because we shrink it all the way up. So we are literally touching the conductor on both sides. All right. Here's the punchline. The punchline coming up. Can't find back my way when I go back down. Here. So E normal on one side is equal to E normal on the other side. This is what we say. No. Okay. We said this already. 2C is in the conductor, so E equals 0. But outside, BC, which we call B2, is free space. So C, B to C, dl B to C, B to C, dl, B to C, dl is E normal times delta H, which is almost 0. C to B E normal, hold on, C to B dl is B to 2, that is B to the conductor, and 2 to C, 2 to the other end of the C to B is C to 2 plus 2 to B. Which is this. And C to 2 or B to 2 is delta H over 2. Okay? So C to B or B to C equal En delta H over 2. And A to B equal minus En delta H over 2. This works out to the tangential component of an electric field from the conductor to free space is equal to 0. So E tangential is 0. So D tangential equal epsilon naught E tangential is 0. So that's not in here, but E tangential for electric field from a conductor or across a boundary with air is 0, which is this. Now, if we go back and look at the pillbox, we are going to do the same thing with the pillbox. We are going to squish it down like this. According to Gauss' law, the integral of d dot ds is equal to q around the Gaussian surface. We have three surfaces. We have the top, bottom, and the side, or the lateral part. If we squish the pillbox, that delta H approach 0 as we did with the rectangle, delta H equals 0, that means delta H equals 0. So d dot ds at the top the bottom surface is in the, okay, the bottom surface or this surface is in the conductor. So we already said d for the here is 0. So we are only left with the top and the side, the lateral. Right? So we do the same thing. We move the side across. So d normal top equal d normal this delta s. Delta s. So d normal delta s equal q. But we know that q is rho s delta s. So d normal s equal rho s delta s. So d normal is equal to rho s. And E normal is rho s over epsilon naught.
Only just make restart.
Yeah. All right, we're back.
Yeah, man.
I want to write down something now. And so when an electric field go from one medium to the other, E tangential 1 or E tangential in medium 1 is equal to E tangential in medium 2. And D normal in medium 1 is equal to D normal in medium 2. How a DJ there? Yeah? A German backward. So you get that? Electric field going from one medium to the next. E tangential 1 equal E tangential 2.
That we must write down, sir?
Yeah.
Right.
And D normal 1 equal D normal 2. So let me see if you get that. Let me give you a quick example to do. Condition. Give me a quick second. Boundary condition. 74. Oh my. All right. Do this for me. The boundary between two medium lies in the XY plane. The electric field intensity in medium 1 is V1, E1 equal 2AX.
Sorry, I got too fast.
All right.
Just reach a plane.
Okay.
Start from XY plane.
The electric field intensity vector in medium 1
Yes.
is E1 equal 2AX plus 3AY plus 4AZ volts per meter. Determine the electric field intensity vector and electric flux density vector in medium 2.
So after electric field intensity vector, or you say after electric field intensity vector.
Determine the electric field intensity vector and electric flux density vector in medium 2. ER1 or epsilon 1 is 9 and epsilon 2 is 4. All right, so work that for me right away.
No, that's not.
Finish? Anybody finish? All right, at least tell me what you're doing so I can see if you're on the right track.
So can I read about the first part of the question?
Huh?
Can I read about the first part of the question?
I said, the boundary between two medium lies in the XY plane. The electric field intensity vector in medium 1 is E1 equal 2AX plus 3AY plus 4AZ volt per meter. Determine the electric field
There
intensity.
was a 2, 3, 4.
Yes.
Okay.
Determine the electric field intensity vector and the electric flux density vector in medium 2.
Yeah,
Sir.
Hmm?
Since it the boundaries lie on the XY plane, would the Z plane be the tangential? Would the AY plane would be the normal?
No, man, the boundary is in the XY plane, right?
Yes, sir.
So normal to the boundary would be what?
Z.
Hmm?
Z component.
The Z component.
Absolutamente.
All right, sir. Yes.
So the initial thing you told us to write down was this E2 equal
All right. Work with me now. Work with me. If me I go too fast, you tell me. E1 is what?
2AX plus 3AY plus 4AZ.
Don't leave off your units. Volts per meter.
Volts per meter. Yes, sir.
All right. So E1 equal E tangential 1 plus E normal 1, right?
Yes, sir.
So what's E tangential 1?
2AX plus 3AY.
Exactamente. Everybody get that?
Yes, sir.
No,
No,
we
sir.
don't get that.
E equal E tangential plus E normal, right?
Yeah, me get that part there.
Right. So E1 is 2AX plus 3AY plus 4AZ volts per meter.
Yeah, we get that.
So E1 hello?
Yeah, man, go ahead. Oh,
Hello? So E1 equal E tangential 1 plus E normal 1, right?
Yeah.
All right. You are given E1. What is E tangential 1?
Yeah, that part I'm gonna pick up.
E1 minus E normal.
Eh? E1.
Would have E minus E.
E1 equal E tangential 1 plus E normal 1. Based on the equation that you have for E1, what is the tangential component?
Sir, whatever.
What is the
E1
tangential?
minus E normal.
Eh?
So whichever plane the medium lies on would be the tangential.
Exactly. So what is it?
The X and Y plane. So the 2AX plus 3AY.
That would be the tangential one.
Okay.
And what would be the normal one?
4AZ.
Where is Z? Everybody get that?
Yeah.
If anybody don't get it, speak up. Because I not see you, so I can't say you don't.
So the 2AX plus the 3AY, that's the tangential.
Right,
And the 4AZ is the normal.
right. So you have,
One.
you know that E1 tangential equal E2 tangential,
Yes, sir.
Yes,
Mhm.
sir.
right?
Yeah.
So you have E1 tangential is that, and then you have E. So what's E2 tangential?
2AX plus 3AY, same way.
All right. Now,
Fine, normal.
what is the normal one?
ERD.
D.
Oh,
Epsilon naught E1.
Well, you have a relative permittivity of 9, so it would be ER1 epsilon naught times E normal 1, right?
ER1
E naught
Times
times
E1.
E normal 1, right?
No, come again. Repeat that part there.
All right. D normal,
Right.
D normal 1 would be epsilon times E normal 1, right?
With E naught times ER1.
Yes.
Yes, yes.
Everybody have that?
That is a DN1.
Right.
Mm-hmm.
Everybody get that?
There's a ER1, epsilon naught times ER1.
D normal 1 equal epsilon R1, the relative permittivity, which is 9, times epsilon naught, because remember, D equal epsilon times E, right? So epsilon is E naught times ER, which is the relative permittivity, because E naught is for ear.
Vacuum.
Yeah.
You have that?
Yeah.
So D naught or D normal 1 would be 9, which is ER1,
Time epsilon.
times epsilon naught times 4AZ.
So what's the value for epsilon naught again?
Oh, again.
8.85 times 10 to the negative 12.
8 point what?
8.85 times 10 to the negative 12.
Times 9 times Z4AZ.
Mm-hmm. All right, nobody work out that the long number then. Just put 36 epsilon naught AZ.
36.
That is the 4 times the 9.
Yeah.
Epsilon naught.
Is it? All right, fine.
All right. So you have D normal 1, right?
Yeah.
And
Sorry.
you have E tangential 1, and you have E tangential 2, and now you have D normal 1.
Yeah.
Equal D normal 2.
So D normal 1 equal what?
D normal 2.
D normal 2. So what's D normal 2?
The same value you get from before for D normal 1.
Okay. So what's E normal 2 now?
That value divided by epsilon naught.
Times epsilon R2.
R2, yes, sir. Now, so what's the value for epsilon R2?
Oh.
4.
Hold on.
Never get the full question.
Or
So with the D normal 2, right? You use the epsilon naught times the 4.
Right.
Oh.
What's E normal 2?
Hold on. Then this one was 4. 16.
No, sir.
Yeah,
9, sir, 9.
You have
Okay.
36 epsilon naught AZ divided by 4 epsilon naught.
Oh.
what?
all
Wait,
right.
hold on it. That's fit me. D normal 1
It's 36 epsilon naught. Is it?
is 36 epsilon naught AZ.
And that is equal to D normal 2.
Uh-huh.
But you said the other medium, the ER, is 4.
Right.
And divide that by 4 times epsilon naught.
So 4 epsilon naught E normal 2 equal D normal 2.
4.
There's a 9 AZ.
Yep.
4. Something must slip me. D normal 1 is 36 epsilon naught AZ. D normal 2 is the epsilon normal, epsilon E R2.
No, D normal 2
Mm-hmm.
equal epsilon R2
Mm-hmm.
times epsilon naught times E normal 2.
D normal 1, sir.
D normal 2 equal epsilon R2 Just say it one more time. Let me write it.
D normal 2
Yeah.
equal epsilon R2
Epsilon R2. Yeah.
epsilon naught
Yeah.
times E normal 2.
Oh.
Times E. Or, yes, E normal toward D. E.
E.
E as in
D
Yeah,
normal.
that's one.
Remember, now D equal epsilon times.
what formula there?
Yeah?
The formula there up there, sir, brother, sir.
They want to do that from selfish a single host that man.
The band there, sir.
I like that we do that still. Sure. Remember, from way back, we know that D equal epsilon times E. And epsilon equal ER2 times epsilon naught. Epsilon equal ER times epsilon naught. But right now we only dealing with the normal component because we know the normal component of D1. We know and we know that the normal component in medium 1 of D is equal to the normal component of D in medium 2. D normal 1 equal D normal 2. So what is E normal 2?
So the 9AZ.
9AZ. Everybody get that?
Yes, sir.
Get 9AZ.
Anybody can help me out?
It would be the 36 epsilon naught AZ divided by the 4 epsilon naught, so 9.
Yeah.
I think what you mix up is when you're saying the D normal, them are mixed up with E normal. So you have to make them know say D normal, D as in dumpling normal 2 equal epsilon, which should have be ER2 times epsilon naught times E as in Everton normal 2. So forget Everton normal 2. So that will be dumping normal 2 divided by ER times epsilon naught.
Oh. Okay.
You get it
That's
though?
really E normal 2 we are fine.
Right.
Oh, that's a much man E normal 2 we are fine. So you substitute forget okay. Yeah man, that I missed. Alright, fine.
We're good now.
Yeah.
Yes, sir.
So
Yeah.
what we have already? We have E tangential 1, we have E tangential 2, we have D normal 1, we have D normal 2, and now we have E normal 2.
So we can find E2 now.
So yeah, you can find now. No, you can find D tangential 2 now.
Okay.
So we find E tangential 1. Find D normal 1. Find E normal 2.
So now we have to find dumpling tangential 2.
So we need find E normal 2. So D normal 2.
What's the formula for finding tangential? Right? D tangential.
So we find D normal 2 already?
Yeah, man.
What we use?
Then we just find
Find a while ago.
D
Or the
normal.
E's?
We find E normal 2. And we have D normal 2. And we have D normal 1.
Oh, it's a D normal 2.
would I keep the epsilon naught in it, right? And the answer for
So,
D.
so D, we don't have D tangential 2.
The formula to find that.
Epsilon R, epsilon naught E tangential 2.
Mm-hmm. So epsilon R is 4 times epsilon naught. And what is E tangential 2?
2ax plus 3ay.
Right. So you can find D tangential 2 now. And what that is?
So would I keep the answer in terms with the epsilon naught in it, right? Instead of just
Yeah.
work with it.
Yeah, keep it with it.
So 8ax, well, epsilon naught times 8ax plus 12ay.
12 epsilon naught AY.
Yes, sir. I factorize out epsilon naught.
Mm-hmm. Everybody get that?
Yeah, me get it.
Will you get again now?
Factor out epsilon naught and then multiply it by 8ax plus 12ay.
Okay, yeah.
So I get it.
And
So
that's
what-
D tangential 2.
So what's E2 now?
E normal 2 plus E tangential 2.
And that equal to what?
2ax plus 3ay plus 9az.
Units?